To get some intuition about line integrals of vector fields, imagine a vector field f describing the flow of water in a river. If we were to swim in the opposite direction of the current, then this would require extra effort. Since f is extracting extra work from us, we would say that f does positive work, or negative work rather, because it's extracting work from us. We're moving in an opposite direction. If, on the other hand, we swim in the direction along with the current, the same direction, now the vector field is helping us out. It requires less effort to make progress. So here we say f does positive work. So what the line integral measures, the line integral of vector field f along curve C measures the total net work done by f to an imaginary particle traveling along C. Given a vector field f and a curve C with smooth parameterization in R of t as t goes from a to b, how do we set up the integral? Well, we start with the vector field f with R of t plugged in, and this tells us what the vector field is doing at the point R of t. The other important quantity is where the curve is heading and how fast. R prime of t, this gives the speed and direction of the curve. So this tells us what the vector field is doing, this tells us what the curve is doing. We want to combine these two quantities in an expression that's positive when they're pointing in the same direction and negative when they're pointing in opposite directions. And we have an operation that does just exactly that, the dot product. This expression is like an instantaneous work done at the moment t at the point R of t. So to find the total work, we'll integrate this over the whole curve. And that is the line integral. There's another way that this integral is frequently expressed using the component functions of the vector field f. So if f of x and y has this function p of x and y for its first component function and q of x and y for its second component, which could be written pi plus qj, then an alternate way to write the integral of vector field f over curve C, it's often written like this. So the integral over C of p dx plus q dy. So this means exactly the same as the formula we had before. It's just expressed using the component functions of f. Sometimes these integrals appear separately. So you'll sometimes see where we're integrating over the curve just one component of the vector field. And what this means exactly, this is the integral t goes from a to b, p of with x of t, y of t. That's what you get when you have r of t plugged in, and then times x prime of t, and then dt. And then this one means integral t goes from a to b, q with r of t plugged in, y prime of t dt. So alternate notation, this means the same as the previous integral, but these integrals sometimes appear by themselves. This one means the integral of p with x of t and y of t plugged in for x and y times x prime times dt. This is just short notation for this expression. And similarly over here. Time for an example. Given the vector field f, which takes in 3 variables and has 3 component functions, x of x, y, and z, has x plus y squared in the first component, xy in the second component, and y plus z in the third component, we want to find the integral of f over c, where c is a curve with this parameterization. R of t is t squared, t cubed minus 2t. T goes from 0 to 2. All right, here's our formula. This integral is equal to the integral as t goes from a to b, f with r of t plugged in, dot product with r prime of t, dt. That's just the formula. So I see that we have a few things to compute. First, let's find f of r of t. So this equals the vector field f, except we're going to replace x with x of t, which is t squared. We're going to replace all the y's with t cubed, and we're going to replace all the z's with negative 2t. And that equals, after a little bit of simplification, t squared plus t to the 6th in the first component, negative 2t cubed in the second component, and t cubed minus 2t in the third component. All right, I call that progress. Next, we need r prime of t. That's easy. It's 2t, 3t squared, negative 2. And we take their dot product. It comes out to, again, after a little bit of simplification, this comes out to 2t to the 7 minus 6t to the 5th plus 4t. This dot product becomes the integrand in our integral. Integral over c, f dot dr, equals the integral t goes from 0 to 2 of this polynomial. All right, and if you work that out, it comes out to 8. So positive work in this case.